Hello everybody, welcome to the beginning of the Everest Physics Mechanics course. This course has many handouts and video lectures for those handouts that will help guide you through the journey of physics and mechanics. The video lectures are meant to supplement the handouts, and the handouts have many examples and homework problems that you can follow and do in order to help you problem solve many different physics problems. The video lectures will contain explanations of 2 or 3 of the example problems, so that to ensure that you understand what is happening and why we do problems the way we do them. Okay, so the first handout is on kinematics, more specifically kinematics in one direction. As stated in the handouts, kinematics is the study of how things move. So it describes how things move. So for example, an object's position, velocity, acceleration, these all describe the way an object moves. Now before we go too deep into this kinematics, I would like to first talk a little bit about vectors and calculus, or basic calculus. If you feel like you know enough of vectors and calculus, then you can go ahead and skip a little bit of my explanation. But for those who are unfamiliar with vectors, a vector is essentially something that describes or a vector is essentially something that has a magnitude and a direction. And this can be used to describe many things. For example, position, velocity, and acceleration. I'll go ahead and give you some examples of vectors. One example of vector is velocity. So for example, if I had a velocity this way, I can have a velocity with a magnitude and a direction. Now, the way we write vectors there are multiple ways to write vectors. One of the ways we write vectors is something like this. Maybe we have a velocity of 3 meters per second, 4 meters per second. Now, what this means is that there is a component of velocity in the x direction of 3 meters per second, and a component of velocity in the y direction of 4 meters per second. And these kind of add up to make this vector. Okay. Another way to write a vector might look something like this. I hat 3 meters per second times I hat plus 4 meters per second times j hat. And I hat we just this is just another way to write the vector 1, 0, and j hat is a way to write the vector 0, 1. And this is in 2 dimensions, by the way. So if it were in 3 dimensions, then there would also be a k hat, which would be 0, 0, 0, 1, and so on. Yeah, this is just some basic ways to write vectors and what they are. Okay. So now that we know a little bit about vectors, and by the way, to add vectors, we just add their components. There are a bunch of different operations we can do on vectors, which we will go into later. But for now, this is the basics of what you need to know about vectors in kinematics. Alright, now let's talk a little bit about calculus. Calculus is essentially the math of instantaneous things and limits and slopes and stuff like that. So let's look at a quick example of calculus at work, I guess. So one use of calculus in physics is, for example, the definition of velocity. We define velocity to be the derivative of position with respect to time. Now, if you're unfamiliar with calculus, you might not know what a derivative is. So I'll go ahead and give a brief explanation. A derivative in single variable calculus is essentially the slope of, I guess in this case, position with respect to time. So, for example, if you think about a graph of position of position versus time, we might ask, what is the velocity of this point at t equals 0? Well, you might have learned that velocity is change in position over change in time. So if you want the instantaneous velocity, quote unquote instantaneous velocity, at t equals 0, then what we would do is we would take, let me undo that real quick. We would take the limit for some change in t. We would take the limit as that approaches 0 of the change in x over the change in t. And what we mean by delta t approaches 0 is that we take some, or like let's say we take some delta t, we would essentially shrink this delta t until it becomes maybe not quite 0, but it becomes very close to 0. And in doing so, your velocity approaches from a reasonably good approximation to a better and better approximation of the instantaneous velocity at that point. Okay. So that was derivatives. I would also like to go over integrals. In single variable calculus, you can think of the integral. Let's make a graph here real quick. You can think of the integral of a function as essentially the area under a curve of something. Let's say 0 to I'll call it like a. So if we want to take the integral from 0 to a of v dt, essentially what this means is that we start from 0 and we go to some upper bound a, and we find this area here. And that is essentially what an integral means in single variable calculus. Of course, this is a very basic explanation, and it gets a little more complex than this, but for now, this is what you need to know for kinematics. Alright, so that was a little explanation on basic vectors and calculus. If you didn't understand that too well, it's fine. There are plenty of online resources for basic vectors and calculus for physics, and of course, you can always contact an instructor if you need help. Alright, so let's go ahead and go over this problem on, kinematics, so position, velocity, and acceleration. We are given a particle that moves in the plane, and its position is given by this function. And we wish to find the position, velocity, and acceleration of the particle at time t equals 3, and the average velocity and average acceleration over t equals 0 to t equals 3. Alright, so let's do the most simple one first, probably, the position of the particle. To find the position, we can just go ahead and plug t equals 3 into here. We're given that x equals 3 times 3 cubed minus 5 times 3, and y is equal to 3 squared minus 3. And if you compute this, it turns out that you will get the vector 66, 6, which is also equal to 66 I hat plus 6 j hat, if you prefer. And you can think of this on the xy plane. Oh, I can't draw. You can think of it as the particle is at some position. This is like the vector 66, 6. Right. Okay, let's move on to the next thing, which is velocity. More specifically, instantaneous velocity, since we want to find it at t equals 3. So, remembering from our explanation just now, or our explanation of calculus just now, velocity is defined as the derivative of position with respect to time. And, I guess I shouldn't use x. The derivative of position with respect to time. Yeah. And the way we take derivative of polynomial functions is we can make use of this thing called the power rule, which states that the derivative with respect to, I'll say time t, of some power x to the n is equal to nx times x to the n minus 1. And you can think, right, let's say that this is the function x to the n. The slope at any one point is given by n times the value of x at that point to the power of n minus 1. Okay. So yeah, knowing this, we can go ahead and calculate the velocity. The derivative of our x position is equal to 3 times 3t squared minus 5. Well, I guess times 1 times x to the naught, or times t to the 0, which is 1, comma 2t minus 1. And if we go ahead and plug in t equals 3, then we can calculate that this is 3 times 3 squared minus 5, comma 2 times 3 minus 1. And if you compute this, this turns out to be 76, or sorry, not, there should be an extra 3 here. This turns out to be 76, comma 5. Or you can write it with I hat and j hat. For the acceleration, it's very similar. We just take the derivative of our derivative, the derivative of the velocity. Our velocity was given by 9t cubed minus 5, so the derivative, or sorry, 9t squared minus 5, so the derivative of 9t squared minus 5 is just 18t, and the derivative of 2t minus 1 is just 2. So, or sorry, no, or sorry, yes. Now, if we plug in t equals 3 here, we get that this is equal to 54, comma 2. And yes, this is the acceleration at t equals 3. Alright. Now for the average velocity and average acceleration, which is slightly different. The average velocity means the velocity over the entire interval. So for the average velocity, we can just take x of 3 minus x of 0. This is just standard finding a slope over 3 minus 0. And, or sorry, this should be, yeah, okay, well this, comma, and then like y of 3 minus y of 0 over 3 minus 0. And if you compute this, which which I won't do, but if you compute this, you will get, I believe you'll get 22, comma 2. Alright, so now let's go ahead and go over this example 1.12. You should note that I did skip over a lot of the problems. Again, this video lecture is meant to go over basic problems to make sure that you understand the material, but please do use this video as a supplement to the lecture notes, or sorry, to the handouts, and be sure to go through and do the example problems. Probably try by yourself first, and then you can look at the solution for all the problems that aren't covered in this video. So yeah, make sure you go through the entire handout. Alright, so this example makes use of the kinematics equations. And so what the kinematics equations do is they take time, position, velocity, and acceleration, and they relate them to each other. And we can see that in this problem. So first of all, let me go over what the kinematics equations are. The first equation states, I'm listing these in a different order than how, but the first equation states that the final velocity of an object minus its initial velocity, so the change in velocity, is equal to acceleration times time. And this is just basically straight from the definition of what acceleration is. Acceleration is change in velocity over change in time. The second equation states that the displacement of an object is equal to initial velocity times time plus 1/2 times the acceleration times the time squared, so 1/2 at. And this can be used through this can be derived through a little bit of calculus. But yeah, you can just take that as is for now. The fifth equation is similar to this, except in this case we use VF instead of VI, and we subtract 1/2 at squared. The third equation states that the final velocity of an object squared minus its initial velocity is equal to 2 times the acceleration times the displacement, and the fourth velocity, or the fourth equation, states that displacement is basically equal to average velocity times time. So why do we have these 5 equations? Well, you might notice that for a general kinematics problem, we usually have 5 unknowns, mainly time, displacement, initial velocity, final velocity, and acceleration. And I should note that acceleration, in order for you to use these kinematics equations, the acceleration has to be constant. Okay. So now, we have all these. So why do you have these 5 equations? Well, you might notice that equation 1 is missing displacement. Equation 2 is missing the final velocity. Equation 3 is missing time. Equation 4 is missing acceleration, and equation 5 is missing the initial velocity. So what this means is that if you are given 4 facts about an object, 4 facts about the object's kinematics and movement, then you can automatically find the 5th variable by using one of these equations to find out that 5th variable. Alright, so now that we've gone over the kinematics equations, let's go ahead and look at this problem. We have a deer that is running at a speed of 8 meters per second, and the bear sees the deer when the deer is 20 meters to the north. And that now the bear starts at rest and it becomes chasing the deer with its constant acceleration. And we want to see what time the bear catches the deer. Right, now there are many ways to solve this problem. I encourage you to give this video a pause and go ahead and try the problem yourself. Wait for a few seconds. Make sure to pause the video and give this problem a try. But if you're back, I'll go ahead and go over the solution the handout uses. So the handout, okay, let me first draw a diagram. You have a deer running at 8 meters per second, and a bear, 8 meters per second, and a bear chasing it with an acceleration of 2 meters per second, and it begins at rest, and it's 20 meters to the north. Okay. So the solution the handout uses is to say, we can first find out at what displacement the bear catches the deer, and from the displacement we can find out the time it takes to catch the deer. Okay. So, first of all, the position of the bear is equal to 20 plus the position of the deer. And that's just because it starts out 20 meters below the deer. And S stands for the distance the bear and the deer travel when they meet. Okay. Now we can also write by the kinematics equations the displacement the bear travels is going to be equal to its initial velocity times time, but its initial velocity is 0 since it begins at rest, plus 1/2 times its acceleration, which is 2 meters per second. I'll just write 2 times t squared. This is equal to just t squared, and I guess you would write times times like 1 meter per, or sorry, yes, 1 meter per second squared, but I will omit that for now. Okay. Now we know the displacement the bear travels in terms of t, so let's figure out the displacement the deer travels in terms of t. Well, the deer has no acceleration, so for the deer, it's the displacement it travels is just equal to velocity times time, and we're given that the velocity of the deer is 8 meters per second, so s deer is 8t. Now if we go ahead and plug these in, we will get that t squared is equal to 20 plus 8t, and this is a quadratic, and if you solve this, you get that t equals -2 or 10, but clearly we can't have a negative time. The deer is not running backwards, so our answer is 10 seconds. Alright, so now we've gone over this, again, make sure you go through the rest of the handout and make sure you go ahead and try all the examples on your own, so you can really get a solid grasp on the problems. If you ever need help, you can always contact the instructors. But yeah, that will be it for now. So yes, in this video, as a recap, we went over kinematics. We first went over vectors and scalars, and then from vectors and scalars and a little bit of basic calculus, we were able to discuss what the position, velocity, and acceleration of the graph, or we were able to get position, velocity, and acceleration from a graph giving some variables that described an object's motion, and we were also able to calculate values of position, velocity, and acceleration given values, or given other values that we already knew. We were able to calculate the unknown of position, velocity, and acceleration. Alright, so yes, that's it for this video. Remember, give these problems a good try. Good luck on the homework problems, and I will see you later. Goodbye.